Previously. I have a new project, or you will be hit. I guess this is the coin holder, maybe? I don't know what this even is for. It does look like there is a fuse missing. Oh, that's not good. Alright, that's definitely not good. Well, it's unfortunate, but I think this entire wiring loom has to be removed because they're all sort of interconnected. So I'm going to label all of these plugs and jacks and make sure that I can put them back in the right place. And then I will just plug in the things that I need to. The wires just go all over the place. Okay, now that I've removed all the plugs from the main transformer and power supply, I can just unscrew this from the base and remove it and examine it and test it and make sure everything is working okay. There's not a whole lot that can go wrong with this thing, considering that provided there's nothing underneath, this is just a transformer with a big capacitor and a bunch of fuses. But let's take it out and see. Okay, well, looking underneath the device, we can see that there is a bridge rectifier here. These are where the fuses are. That's the capacitor, the transformer. There's an EMI filter over there, and what appears to be just a bunch of connectors over here. So, again, not a whole lot. That would be a DC power supply with a huge filter capacitor on the end. So let's just, hook it up and carefully, without touching any of the metal bits, see if this is actually outputting what it should be. And so here's the schematic for the power supply. We can see that AC comes in here and goes through a filter here, and then it goes through a jack which is connected to the interlock switches, which are the buttons that go to the front and back door to make sure that the power turns off when you open up the cabinet. And then the power goes up to this voltage selector, and you can see that there are a bunch of different voltages that you can apply to this power supply, but it all comes out as 120 volts over here. And in fact, there's a little tap over here that you can tap off and get 120 volts AC regardless of what you're inputting. So there you've got the transformer. Interestingly, there's a little thermocouple here, which is interesting. So I guess if the thermocouple goes off, and this says 110 plus or minus 5 degrees C, then the thing turns itself off. So here we have the outputs. Starting at the bottom, it looks like we've got 60 volts AC and another 60 volts AC circuit. We have here a fused circuit which gives 6.1 volts AC. We have another fused circuit here which gives 36 volts AC. And then finally we have a fused circuit here which goes through a diode bridge and a filter capacitor, which is going to supply 10.6 volts DC. And of course that's probably going to have a lot of ripple because it's just a single capacitor on the outside. So what we should do is hook up the interlock switches and then turn the switches on so that we can power the power supply up, and basically just measure these voltages. And I don't really expect anything to go wrong with this, so let's see what happens. So I've hooked up the multimeter to the auxiliary AC out that doesn't output power until all the safety interlocks and the main power switch has been closed. So I can see that I am getting power. So that's pretty good. So now all I have to do is check all of the outputs here. Okay, so here we have our 60 volts center tapped. And it is indeed center tapped. So from both ends we get 60 volts, and from the middle to any end we get 30 volts. So let's check the next circuit. again, as expected, we get 60 volts AC, and now if we go to the center tap, we see that we have 30 volts. So that's working. Now on this circuit, we're supposed to be getting 6.1 volts. 6.4 is probably just fine. And here we're getting the 36 volts AC, and it is indeed center tapped. If I move one of the probes to the center, we do indeed get 18 volts. So, the final thing to check is the DC voltage. Okay, and here we see a DC voltage of 13.8 as opposed to the 10.6 specified over there. This has a number of reasons. The main thing is that there is no load on the system. And the other thing is that this is probably not a very clean wave. In fact, let's see how much ripple there is. Not really a whole lot, so, there's basically no load being drawn from the capacitor, so there's very little ripple happening, which means that we are at 13.9. Now, of course, as you add more load, that would go down. And presumably with the machine fully on and everything connected, that would be 10.6. So I think that we can say that this power supply is working perfectly fine. I don't see any problems with the capacitor, so we will just leave it in place and not replace it. And of course, because it's just a capacitor with no load connected to it, when I do turn off the power supply, the capacitor very slowly discharges basically through this multimeter. So I could just leave it. 13 volts is not lethal. It's only when you get to about 48 volts or so that things get lethal. So there really is no danger here, except maybe a fright if I happen to short the capacitor terminals. Now, while I've got that capacitor discharging, the next circuit that I'd like to go into is this regulator/audio board. And we can see that we have the 10.6 volts going into the system, along with 36 volts AC. And output, we have a whole bunch of regulated voltages. So we've got, for example, a +5 return, we've got +5 regulated, and we've got plus and minus sense. So that will tap off of some system to make sure that we are actually outputting 5 volts. And the regulator gets adjusted according to that. We have 2 audio inputs, and then it looks like we've got, I think this is probably a bunch of outputs. We've got -5 volts DC, -22 volts DC, and +12 volts DC, and +22 volts DC. And then down here, it looks like we have speaker 1, speaker 2, and speaker 1 return. I'm not entirely certain why there isn't a speaker 2 return, but presumably audio 1 and audio 2 get amplified to this speaker. So this is sort of a combination thing. What I'm going to be testing is the regulator portion of the board to make sure that that is working. And I'm also going to look for that resistor that burned out right over there in order to see what function it has, and I presume that it's not going to be part of the audio circuit. I don't know why an audio circuit would burn out like that. It's probably more like the regulator. So let's take this board out now and just poke around and see if all the capacitors are okay and all the semiconductors are functioning properly. And then we can try plugging it in and seeing if the magic smoke goes out of that resistor. And if it doesn't, well, maybe I have to replace the resistor and
smoke it again. So let's see.
So I'm just visually inspecting the back of the board, and I don't actually see anything bad in particular, with one exception, and that is over here. It looks like there's some flux, which usually means that this component has been possibly replaced at some time, because otherwise, it would have come out of the factory clean, I believe. And if we turn the board over, we can see that that is a heat-sinked 2N3055, which is just a standard power transistor. And I don't really see anything else bad on this board, with the exception of that resistor, which burned out when I plugged in the machine. So we can test a few things. For example, there's a diode right over there. There is a transistor. Here's another transistor. So we might be able to test all those and see what happens. In addition, I can look at some of these capacitors a little more closely to see if they're leaking. Just at first glance, they don't appear to be leaking, but what does worry me are the semiconductors mainly on this board. And why did R29 get so much current through it that it blew out? I can take a look at the schematic and see what might cause R29 to blow. Here we see the schematic for the regulator and audio board. At the bottom of the schematic, we can see the two audio inputs going through pretty much identical circuits to the two speaker outputs. And we can also see that there is actually both a speaker 1 and speaker 2 return, and those are actually connected. So that's not interesting at this point. What is more interesting is the top of the schematic, which shows two separate power supply circuits. Let's take a closer look. Here is the first power supply circuit. It's taking 36 volts AC, referenced to the center tap, and it's putting it through a few input filter capacitors, a diode bridge to convert that to DC, and then a few output capacitor filters, along with bleeder resistors, so that when the power is turned off, that bleeds off the voltage here. And it looks like these are spec'd to be 35 volts, so of course 36 volts AC is going to end up being a certain amount of voltage. And if we take a look at where that goes, well, the positive side goes through a small resistor and then to a 7812 volt regulator, which is a positive 12 volt regulator. We've got another filter, input filter and output filter capacitor, and that goes out to plus 12 volts DC. And we see that we're actually tapping off this, which says it's going to be 22 volts DC, and of course that's going to be unregulated while this is regulated. Same thing with negative 22 volts DC, that's the raw output from the bridge, and that goes through a small resistor, through an input filter capacitor, a 7905, which is a negative 5 volt regulator, an output filter capacitor, and out to minus 5 volts DC regulated. So the resistor that burned out was R29, which is not in this section. So we can go to this next section over here, where we see the 10.3 volts unregulated DC coming out here, along with the signal ground. So that would be the negative, that would be the ground with respect to 5 volts, which is separate from, I guess, the rest of the noisy circuit ground, which I suppose is a good thing. This right here is an LM305, that is a general voltage regulator. Without going through all of this stuff, you can see the data sheet online. Basically, these transistors are driven by Q1, the voltage regulator, to regulate the amount of current that's allowed to go through these transistors. So this is a small transistor, this is a power transistor. This diode over here is to prevent, well, I'm not sure what it's there to prevent, but it's there to prevent something. This diode over here is also to prevent any positive voltage from being passed from essentially the ground to the plus 5 volts rail. In other words, it's to prevent the voltage from being reversed somehow. And these are the outputs. So we've got plus 5 volt regulated and the plus 5 volt return, which is the equivalent of ground. So that's this signal ground. And we've got plus and minus sense, which basically you run the line from the output of your power supply all the way to where you're actually feeding 5 volts, and then you sense that voltage over here. And this should be actually very low current, so that there's not a lot of ohmic loss in the line that you're tapping off of. Same thing with the negative sense. So we can see that there's our 29 right over there. It's a 10 ohm resistor, and it appears to be connected through a voltage divider over here. The voltage divider is tapped off of, which provides feedback to the LM305 voltage regulator to regulate its voltage. So of course you would set that until you got 5 volts on the output. So the problem appears to be that this 10 ohm resistor burned out. The only way that I can figure that that resistor can burn out is if the positive sense were actually grounded. If it were grounded, then you would get 5 volts here and 0 volts here. So you would get 5 volts across a 10 ohm resistor, which gives you half an amp. And that resistor was in no way capable of half an amp. So basically, it would be voltage times current. So the voltage here is 5 volts. The current would be half an amp. So that would be 2.5 watts of power going through that resistor. This resistor was definitely a 1/4 watt resistor. So yeah, it could not take 2.5 watts. So my suspicion is that the positive sense terminal was grounded somewhere. Now, if it isn't grounded on this board, then I can simply replace that 10 ohm resistor with a new one. Test all the semiconductors, basically just check their junctions for correct diode operation, and that's a really simple way of just making sure that they sort of kind of work. And then just test the board in isolation, connecting basically the plus sense to the plus 5 volts and the minus sense to the 5 volt return line, and make sure that we get 5 volts out. If we do get 5 volts out, then that means that the problem is somewhere further down the line. Otherwise, we've got additional problems somewhere in here. So let's go ahead and do that. So with the resistor replaced right over here, what I've done is I've connected the negative sense to the minus terminal, the positive sense to the plus terminal, and I've plugged in the 10.6 volts input, and that should be enough to get the 5 volt regulator running. So we'll see what happens. Okay, I will turn the machine on. Okay, and so far I don't see any magic smoke. So let's go ahead and measure the output. Okay, so I'm just going to turn it on again because I forgot to plug in the power that actually goes to the board. So, turning it on. Okay, and I'm not seeing any problems yet. But I'm also not seeing any output. Now, that just may be because I'm on the wrong pins. So, what I'm going to do is hook into this ground test point here, and this is supposed to be +5 here, and we are indeed getting +5 volts, so I was just probably probing on the wrong pins on the jack. But in any case, we are getting 5 volts, and I don't see any signs of anything getting hot. Here's the circuitry on the vector generator board showing that definitely minus sense is supposed to be connected to the +5 return, and of course positive sense is supposed to be connected to +5. So let's take the cable harness off and maybe check the printed circuit boards. And here we have the boards are out, along with the schematics. So this is the vector generator printed circuit board, and this is what they call the auxiliary printed circuit board. And there's our lovely 6502. And this is a power LED that's supposed to light up. And another one over there. So let's take a look at this. Here are also the connectors. They felt a bit loose, and I think maybe they're just like really old. But I'll take a look at the printed circuit board itself to make sure that at least these signals are connected the way they should be. And just checking the connections over here, they all seem fine, so I'm beginning to suspect that the conductivity of this harness, or at least this slot, is not that great. Yeah, so I really don't like how loose this is. And I think even cleaning it is not going to be so great. Luckily, from some other ridiculous project, I have these replacements, and they do fit very nicely. Just like that. So I think what I'm going to do is maybe take this wiring harness out and just solder the wires on. So here we are. I have replaced all of the connections and these two connectors with nice new-ish card edge connectors, and I went ahead and looked at these wipers in here under the microscope, and take a look at what I found. So these don't look so good, especially like on this one. You can see that there are cracks starting. Look at how loose that is. I mean, this is practically breaking. Let's see. They're pretty rusty. There's some other like broken ones, cracking ones. Here's a bunch of pitting and tarnishing, rusting. So this really was not in very good shape at all. So I'm pretty glad that I replaced this whole thing. Not good. So I've hooked everything back up. So down here we've got the power supply going to the wall, and then we've got the regulator with the audio amplifier. We've got the two printed circuit boards on the side, and all the way in back we see that there's a speaker over here. This wire over here I think goes to two speakers up at the top of the cabinet, I think. And this wire right over here is the one that goes to the screen, so that's the vector display. So what I'm going to do is I think I'm going to watch the regulated voltage supply, and let's make sure that it doesn't explode when I turn this on. here we go. We don't have any burning. We also have, great, the LEDs on the PCB's lit, so that's good. And I guess the next thing to see is the front. Okay, well we have lights over there, and we have lights up there, but as for the screen, there's nothing. Alright, so the next thing I guess to check is to make sure that the screen is getting voltage. For all I know, the screen is dead. The filament could be toast, the screen itself could be toast, but I guess we'll take a look at what to see next. So we're at the point where we got the LEDs on these printed circuit boards here to light up, which means that the power supply is probably good. So that's great. We replaced all of these connectors, that's great. But when I turned it on, the only thing that happened was that the relays over by the coin slots went off, which is, I guess, good. The lights in the front went on, which is good. However, I didn't hear any sound. I should probably see if there's a video online of a Battlezone machine. Maybe it doesn't make any sound when you just power it on. And there wasn't anything coming out of the monitor. So let's look at the underneath of the monitor section. So this is a driver board which takes the vector inputs and converts them into signals for the CRT, which is up there. It also takes 60 volts AC and does a few things to it, and then passes it on to the high voltage power supply, which is over here, which supplies the 12 or so thousand volts for the anode of the picture tube, which you can see that little suction cup looking thing. We can see there is an LED over there. That LED goes off when there's a circuit in there which basically turns the beam off if there's no signal, because remember there's this is a vector system, so it doesn't scan constantly the CRT. It actually just draws lines on the CRT, kind of like an oscilloscope. And if there's no signal, that would just lead to the gun giving a spot right in the middle and just burning out that middle phosphor. And this LED goes off when that circuit goes off to detect that condition, and that results in the beam being turned off. Now, interestingly, there's a whole bunch of fuses here. There's one over there, there's one over there. There's a bunch in the corner, and you can see that there's actually 2 fuses missing. That's not great. So here is a view of the placement of the components on that board, and this is oriented the same way we were looking at it. There's that LED over there. Here are the 2 missing fuses. So it says F100 and F101. Let's take a look at the schematic to see what they do. So here is the schematic, and here are the inputs. Now, the interesting thing is, if we zoom in to here, we see that F100 and F101 are the input fuses for 60 volts AC. This is the X input over here and the Y input over here. Without that 60 volts AC, this thing isn't going to do a whole lot of anything. Because for one thing, let's see, it looks like it gets rectified by a full bridge rectifier, and then there are some capacitors, and they sort of go all the way over here. There's another fuse over there, and there goes to the external high voltage, I guess. But in any case, yeah, without those fuses, we're not going to get any voltage at all. So That's kind of, I wonder why they were removed. Maybe, just because when they put it in storage, they wanted to make sure that it wasn't powered up accidentally. I don't know. But I'm going to replace them and see what happens. Again, I didn't see any leaky capacitors or anything, so it'll probably be okay. Maybe. We'll see. Okay, so I received the fuses in the mail. Now, these are the ones that are missing. There are just two 5-amp fuses. They're all slow blow type. And these are the 5-amp ones, but there's also a 1-amp fuse here and a 2-amp fuse here. These are already in there, but I figured that I may as well get those just in case they blow. That's in addition to all the other fuses that this thing takes. This is a 7-amp one, here's a 20-amp one, and here's the 4-amp one. So that goes to that power supply over there. So what I'm going to do is pop in these fuses, turn the machine on, and hope the fuses that I just popped in don't pop apart. Pause for laughter. Okay, so with the fuses in place, now the only difference is that we have 60 volts AC coming from the power supply going up, let's see, this wire here, up to that jack, and over to this circuit here, which in turn feeds that high voltage power supply, which goes to the anode of the CRT. So, let's turn it on and see if things happen. All right. Whoa.